All right. So welcome back. This was the fun part. The bad news is now it's the less fun part, not because it's less entertaining, hopefully it is, but because it will be longer. We have 90 minutes for the non-practical session, but I realized that I didn't get very far. And if you agree, we use some time of the practical session to finish the slides off, and then use maybe half an hour or something for the practical session. At any time, say if you don't agree. But let's see how quick we progress through things. Doesn't mean, however, that you shouldn't feel free to interact and interrupt whatever at any time. So we've last been talking about the different feature set sizes and the different challenges. I just wanted to show that from 2009, 400 features, 2010, 1,600, 4 times more, to 2011, 4,000, it's 10 times more than the original feature set, and this year even 6,000 features. Is it worth it at all, or is it just, well, for the sake of producing impressive numbers? So we looked at this in the 2011 challenge, and we ourselves looked at it repeatedly. Of course, we're not making new feature sets if they're not better than the last ones. So for intoxication and sleepiness, you can see from the 400 features up to the 4,000, you get some 5% gain in weighted accuracy and some 2% here for the unweighted accuracy. By the way, I never talked about unweighted and weighted accuracy. This is one of the major confusion in the challenges. What is unweighted accuracy? It's simply recall from one class plus recall from the other class divided by 2, meaning that we have a 50% chance level, and we know what the chance level is, whereas if you use weighted accuracy, which is your normal accuracy, which is simply number of correctly classified instances divided by total number of instances, you don't know what is the chance level. Say if you want to recognize rainy or sunny days in London, and maybe it rains 9 times out of 10, which is not true, but let's assume it were, you would have 90% accuracy by only saying it rains without even classifying. So we always use unweighted accuracy because it tells you what really works. If it's above 50%, something works. Otherwise, we don't know because we don't know the chance level. Now, this is just one example of such a feature set because I've shown the principle. What does it look like? Here are some functionals, 33 for the 2011 feature set. So, for example, mean of peak distances or duration. Signal is below 25% of the range. This is the low-level descriptors. So, for example, sum of auditory spectrum, 0 crossing rate, MFCCs 1 to 12, jitter, shimmer, and things like that. And then each functional is applied to each low-level descriptor, and this is how you end up with the 4,000 features. And then, of course, you wouldn't want to use all these features. For the baselines and the challenges, we always do because we don't want to optimize or don't want to over-optimize. This is what the participants should do. We rather want a very transparent and redoable baseline. But in a study by yourself, you might want to do that, and you can use PCA, LDA, filter-based or wrapper-based search. So you're either searching for the best features with the classifier in the loop and see which gives the best accuracy, which feature set. Usually you can't do this exhaustively because you're having 4,000 features. So you need a suited search function. One of the most popular ones in this field is sequential forward search. So you're starting with an empty feature set. You see which is the first individual best feature, then see which is the best to add to that, then see which is the next best to add. If you add floating, you always step 3 steps forward, maybe 1 step backwards, 3 steps forward, something like this. So you see, once you have 3 features, you see, would it have been better to have added another second feature to this set as far as I have it? Of course, they're always suboptimal and they're more or less efficient, but you can't afford exhaustive search. The filter-based is simply using some measures like information gain. So how much correlated is it to the class label, my individual feature, or which information gain is in this feature? That is usually very, very fast, but of course not as much tailored to the classifier as the closed loop one. And then you could also elaborate on the feature space, for example, by genetic feature relevance analysis, where you have some feature set, and you allow for some random operations, for example, crossing of feature sets. So you exchange in the middle of the feature set from another subset of the features and see if this new subset is better. You can, by permutation, turn on and turn off features within the feature set and see if it gets better by that. So you're simply injecting chance or random. But now comes the real generation of features, where you add new variants of the features by chance. So for example, feature A divided by feature B, or feature A logarithmic representation, and then see if it gets better by that. But the problem with that is you're having 4,000 brute force features, and if you select the features like this, you will end up with the best feature set being MFCC 1 divided by MFCC 2 means, or the mean of the maxima of the DCT coefficient of pitch, something like this. So what does it tell me? Probably nothing. It's highly over-adapted to the data set that you were training on and selecting features on, and you can't interpret things. So what we're usually trying to do is rather do a horizontal and vertical scan, how we call it. So we're scanning by low-level descriptors and by functionals and see which functional is best. Often we figure that the very simple functionals are best, so the means rather than the kurtosis or skewness in terms of moments. And then by feature grouping, we can even reach a more meaningful and compact representation. For example, here, grouping all duration features, all energy-related features, all F0 features, something like this. And from this perspective, we can reach interpretation in two ways. One is we see how many individual features were chosen in a feature selection from this according group, or we could see a group-wise accuracy, what is the best performing group. So for example, here you're having different databases for emotion or interest, and the major cover groups were, for example, prosody, spectral, and voice quality, and the most features were always selected from the spectral feature type, some 80 plus %, almost none from voice quality, and only few from prosody, which is a surprise to many people working on speech synthesis, because there you would say speech prosody is the most important in synthesis of speech to sound very emotional. But here in analysis, apparently prosody is not determined reliably enough, or it's too naturalistic, the audio, and spectral simply gives you a good, robust representation. Now, the other way to look at it is by accuracies, and we have the same groups, and you can see that prosody is somewhat similar then, 75%, maybe 70%, to spectral features, 80 or 79%. And there's another reason why so many spectral features have been selected, simply because there are way more spectral features. If you're having MFCC 0 to 12, you're already having 13 LLDs, whereas pitch is only a single one. And if you brute force from these, of course, the effect multiplies. Okay. So then you could even select features through time. For example, see are the global features better than the features from smaller units, time units, like fixed time intervals. So compare global with segmental or hierarchical, where you combine functionals or functionals. But the main message is feature selection on all original features is not very meaningful, hard to interpret usually. It's overfitting severely the data case, whereas some meaningful selection is usually preferred by us, going by low-level descriptor type, by functional type, or by time level. What we're dreaming of is to learn the features more and more. You've seen that we're learning the model, we're clustering sometimes already. And the idea would be to do maybe as the human does. The human has some sort of time frequency representation from a filter bank, and then by himself learns or herself learns what are the right features. We started a little bit by using deep neural networks, restricted Boltzmann machines, to project the space to 2 dimensions. So we have the large feature space, and instead of using a PCA or something like that, we use a deep neural network and learned the optimal 2 features and had some 9 databases for evaluation, and had the support vector machine with the original feature space and with the 2 features only, and we had always an improvement of 2 up to whatever, even 10% depending on the database, meaning that if we had the right 2 features only, we could have a way better representation. But of course, we're still using all the original feature information. And if we had a classification from the deep neural network directly, we wouldn't even need a secondary feature anymore. So it's a little bit tricky if this is really learning the feature space or classifying by the deep neural network. Now, another alternative is a bottleneck architecture, which we started to use recently with our long short-term memory recurrent neural networks. And by that, we could reach the best result on the 2010 effect sub-challenge task for the interest and had some correlation of 0.5. I think the baseline was 0.44 or something like this. And the idea is simply that we have input features from the acoustic side, from the linguistic. So there's an automatic speech recognizer, it produces some linguistic features. Then we have it passing through a smaller layer where the bottleneck, so to say, is, and the network itself learns how to do the feature reduction, so to say. And that gave us some improvement if you look at bottleneck yes or no of 0.47 to 0.50 or something like this. So it's highly significant again. But the idea really is to find suited architectures and more have the system maybe even learn by itself which features to prefer. So from features to classifiers, usually as for the data, we could have many requirements. One is adequate modeling, then optimal accuracy. Most papers focus on optimal accuracy, but of course there are efficiency requirements, economic factors, and optimal integration in the system context. Adequate modeling could be static or dynamic modeling, data or knowledge-driven, handling of uncertainty, learning stability, model instance-based, transparency, and so on. Then optimal accuracy, maybe discriminative learning or automating of features, efficiency, real-time recognition, short learning adaptation time. Economic factors are obvious, low hardware requirements, short learning and adaptation times. And then also optimal integration. This one is hardly of interest in most papers. How can we integrate the output? Does it provide reasonable reliability measures or confidences for a system integration? So we have these many different requirements, and we have many different classifiers to choose from, and we have absolutely, well, almost no standard in the field. So it's not like in speech recognition where you say the hidden Markov models are your standard paradigm, more or less, but it's rather not even settled whether it's dynamic or static modeling, HMMs or neural networks. If there are some very popular ones, it's certainly support vector machines, and even naive-based, so even very simple classifiers are often used, given the small database sizes in the field. But you will find neural networks, you will find trees, random forests, everything. I want to highlight one particular classifier which we believe is introducing quite an additional paradigm. It's not only a support vector machine versus neural net, but they all do the same more or less. And let me first assume that audio is usually sequential. This is why we usually have our hidden Markov models. And we should model the temporal context somehow. But the HMMs are not particularly good at that. So you can think of combining recurrent neural networks with HMMs. But if you look at recurrent neural networks, they have one problem. The recurrent neural network feeds the output back to the input, maybe in the input layer, maybe from the hidden layer to the hidden layer. However, the principle is to have output fed back into the input to model what has been going on beforehand. The problem now is the vanishing gradient problem. That means that the information vanishes over time because there is no storage inside the network. It's only implicitly there because it has been fed back, but it's nowhere stored in the network. Meaning after 10 steps in time, on average, the information is lost. So you're only modeling things which have been shortly beforehand. Now, Jürgen Schmidhuber at our university introduced the long short-term memory recurrent neural networks, which we picked up here. And the principle is you're having the input layer, hidden layer, output layer, and you're having these gates to input, when to input information, when to output information, and when to erase information, and you're having explicit memory cells in the network. So you can keep the information in the hidden layer perfectly stored, and at some point decide to erase it because you don't need it for more than whatever n steps in time. Then you need to erase it. And you can even learn when to output the information. So this really introduces more than architecture A versus architecture B, because it gives you the chance to store information on the network and even to learn how much temporal context is best. So how is it done? For those of you familiar with neural networks, you would usually have your nonlinearity here in the cell and have your neuron in the network. And now we're adding quite a lot more to this. First of all, the cyclic error carousel, which is a simple cell with an auto weight of 1. So it simply stores what is input into the cell by weighting itself with 1. Then we have some gates here, which decide when to open this gate or close the gate for input. So here the inputs decide when to input into the cyclic error carousel. And here the inputs decide when to read or output from the cyclic error carousel. And for that, we need additional neurons, additional nonlinearities that are connected from the other layers in the network that learn by their nonlinearity when to input and when to output. If we do it like this, we can't erase, so we need one more such nonlinearity, the forget gate. And this decides when to erase the memory from this neuron. So basically, you're doing only an architectural trick. You're not introducing something really new, so you can still use backpropagation through time and your standard algorithms, more or less. You're only introducing a very suited topology with these input, output, and forget additional neurons and these gates here and the auto weight of 1. And then you can have your normal feed-forward or recurrent neural network with input, hidden, and output layer and your recurrent connections from any layer back to another layer, and introduce your memory by this topology. So for these neurons in the network, we're now introducing the additional input, output, and forget neurons. And then you're saying, wow, I'm really blowing up the parameter space, because per neuron, I'm adding 3 more neurons. So you can cluster these and have input, output, and forget control gates for a bunch of neurons, so to say. So you're learning when to input, output, and forget for several units and not necessarily for each individual one. Now, this can't warp through time. So we need something to warp through time. And usually this is done by a hidden Markov model. So here you have your DBN visualization of your hidden Markov model. You have your states and you have your observations here. And if you're having your different audio events, say it's emotion A, emotion B, or whatever, maybe these have audio sub events. You have your trellis and you have your Viterbi backtracking, and you go through the optimal path and say it's first audio event 3, then audio event 1, and you're doing the segmentation through time, audio event 2. And this can be done by the hidden Markov model, but it doesn't have the memory inside. So what you can do is have the observations fed also into a BLSTM, into a bidirectional long short-term memory recurrent neural network, so the network we had just looked at, and have this network output its own prediction on the classes, so joy or anger or whatever, and then have an additional feature stream model this neural network output. And by that, you're having the hidden Markov model watch the features, and in a different separate stream, get the information that the neural network gives using or exploiting the contextual information, and you can adapt or learn the stream weight and see which is better to use the contextual estimate or not. And by that, have a very efficient combination of warping through time by the DBN and learning the right amount of context to use. So yeah, DBN, BLSTM, and the 2 different streams. What I didn't mention, you can use the BLSTM in both directions, forward and backward, meaning that you can model past and future context. If you add 2 layers, one processing in this direction, the other one in that direction. So if you don't have to be causal, if you can allow for a short buffer and look into the future, you can also use future context, or you don't. So meaning that you only look to the past, maybe, if you have to be online. If you don't have to be online, you can also look into the future and exploit from contextual information in both directions. Now we want to see, is this really giving something meaningful? And can we even learn how or interpret how much temporal context is used. Say, if you're a psychologist, maybe you're not an engineer, can I use this as a tool that tells me for anger, 2 steps past and 2 steps future are exploited by the network, whereas for joy, 5 are exploited, whatever. So you could even use this as a tool for analysis. Now, to this end, we're looking at the sequential Jacobian. The sequential Jacobian corresponds to the derivatives of the network outputs with respect to the inputs, and it learns or depicts the sensitivity of the outputs with respect to the inputs. But to cut it short, it simply tells us how many time steps have been learned to preserve in the network. And for this, we have one example, the IEMOCAP database of emotion. And we're looking here at time step 16, so somewhere in the middle. So this is the time here. These are the different features. And this is the Jacobian interpretation, so the output sensitivity to the input. And we're seeing that at this moment in time, the network output sensitivity is highest with respect to the input sensitivity. With other words, the network mostly exploits what is happening right about now, of course. Now here we also have negative values. We can use the absolute values and see the sensitivity. And it's not very useful to look at it in a 3D plot. So let's average it over the different features. And we have this shape now where we're looking at what the network learned. So at our current position in time, it exploits mostly the current position in time, of course, but you can see it's not going down to 0 instantly, but going down to 0 slowly, and it is exploiting past and future context, interestingly more future context even than past context in this database. So we had different thresholds over time introduced to decide how many past and future information it uses. This is with the correct order of instances in the database, and this is with shuffled order to see if the order really does matter or if it learns just something for fun. And you can see that it is on average using 8 future. These are the future ones, and these are the past ones. At the beginning, it cannot exploit past ones. But you see the difference. If the data is shuffled in random order, it learns, depending on this threshold, we define only 5 past or future. But if it's in the right order, it learns 8 past or future, meaning that it has a clearly pronounced difference, and it really exploits past and future information. So this is the same for different constellations, valence activations, and different numbers of clusters. And this is always with the correct order of instances, and this is with shuffled order of instances. And there is at minimum a difference of 2 past and future turns, meaning that the network really exploits past and future information. It really does worse if it has a shuffled order. Okay, so in other words, try to exploit contextual information. This is a hot topic in the effective computing community, and there is a lot of looking at context now, but it seems to hold for all the other speaker states and traits, or most of these, and of course in particular for the long term, where we've seen the averaging over several turns, for example. Now just very shortly about testing protocols. Now that we have the classifiers, the most frequently encountered measure, of course, is accuracy. I've already talked about weighted and unweighted accuracy. Then precision and F measure confusions. What we hardly have in this field is the DECT curves or ROC curves, the receiver operating characteristics, like here, which is very common in the NIST evaluation tasks for speaker verification or speaker recognition, which is funny because actually it would be very suited. You're trying to localize angriness, for example. So a DECT curve or ROC curve would be very suited. For some reason, it's not a common thing, probably mostly because of the data sparseness and because of the artificial database constellations in the past, where you had a lot of acted material or not so much realistic data, but it could be considered for future use. If we have continuous class like age or height in centimeters or age in years, you mostly find mean linear error and cross correlation. So for example, mean linear error tells you how many years on average is it mistaken. Cross correlation tells you how well does it correlate with the different ages. Usually we use cross-correlation when the information is rather subjective, because we're not so much interested in the mean linear error, but rather in does it well follow what the reviewers label, because it's not so important if it's -1 aroused or 0.9 aroused, but it's more important that it follows well, so to say. Whereas for the not so subjective task, we usually prefer the mean linear error. So for example, for age or height, it tells you a lot, or it's more intuitive. Then the partitioning, I said a couple of things on that already. Usually you will find a lot of stratified cross-validation simply because there is too little data to use the train, develop, test partitioning only once. Our preference, however, is to have a train, develop, test partitioning, even if you do it cross-validated. So you could have shuffled, which is train, develop, and test, simply because you're having a well-defined partition, everybody can redo it, and you're having a development partition and not over-adapt to the test set condition. And all the challenges have shown that the test results are always way worse than the development set results, clearly speaking for you're overestimating things if you're not having a development partition. Then significance is hardly reported in the papers, sadly. And if people only write, we found significant differences. Yeah, but what is significant? We really try to always provide the test and the significance level. And of course, you can think of Bonferroni adjustment or other additions to that. And then prototypicality. Here we looked at different prototypicality. We looked at using only the instances where 100% of the labelers agreed, or 4 out of 5 labelers agreed, 3 out of 5 labelers agreed. And there's a huge difference between assuming perfectly agreed upon cases, 85%, and agreeing only more than half of the labelers agree at around whatever, 70-something%. In other words, it's really important to keep in mind, is it prototypicalized or not? Is it looking only at the friendly cases, or are we really looking at everything? Yeah, and another issue in this respect is the content, phonetic content dependence. The first databases often have been recorded with prompted speech, and even in the later challenges we had some prompted speech, like the address people had to enter for the drunken data. The question is, what is the influence of having text dependency or text independency? Or in other words, if I knew which text was spoken, could I improve on the task of interest? We looked at this for emotion recognition, and I don't want to go into too much of the details from this table. 3 different databases, stress, interest, and emotion. Where we had 2 groups, the words that frequently appear, the words that do not frequently appear, and using all words for training. And we have matched and mismatched word conditions. So in other words, think of the word the or a. Words like these appear very often in the corpus, and you could have a the model for neutral or anger. Or you could use, independent of the text, all sort of speech that you have. And interestingly enough, it gets better, even though you're having only few instances, but they match the linguistic or phonetic content, if you use these for training as compared to using all data, and given that they're sufficient numerous. From the group 2, from the sparse words, the results were worse than using a lot of training material, even if it's not matched. So in other words, if you're having sufficient training material for a specific linguistic combination, you could benefit from that. Now, if you look at matched versus mismatched, it is striking the difference between the two. Independent of the database, there's a huge difference between matched and mismatched condition, meaning that you're either training on the right sequence of words or the right word, or matching on another sort of linguistic string or phonetic string. So if you're having a database with prompted speech and you're training and recognizing on the same type of prompted material, you're overestimating things, clearly. And if you're not having such a database, maybe you can even gain something by using models that are tailored to the linguistic content. You could even think of per phoneme analysis, but then again, as said, the analysis usually benefits from larger units. So a single phoneme often is not enough. And this is the explanation also a little bit why the synthetic speech is so well suited, maybe, because you can synthesize the same linguistic content and then do text-dependent recognition, so to say. All right. Now, we talked about features, but we didn't talk about pre-processing and feature enhancement. Of course, there are many, many ways to enhance the signal. There are hardly any papers as of now that consider such techniques and report on results. Most of them are for emotion recognition. So the influence of noise reverberation was influenced for emotion recognition, hardly for any of the other tasks like age and gender and so on. I only wanted to mention one spectral decomposition as an example because it's our favorite. You can download this as a tool. It's the Open Blizzard library, the open blind source separation for audio retrieval tasks. And what it does is it takes the audio signal, then has a spectrogram representation, meaning frame by frame the spectral feature vectors, and then decomposes this matrix of the spectrogram over time into two matrices, the activations and the component spectra. So it's a blind decomposition. You don't know what's inside, but you're decomposing it into spectral vectors, which could be different instruments in music, for example, and typical characteristic spectral prints of that, or it could be different phonemes, for example, but typical characteristic spectra. And then you have the activation over time, which tells for each of these spectral components how active is it over time. So if you think of music, you are having maybe a bass drum component, something like this, and your activation tells you attack, decay, sustain, release of the bass drum. It also tells you when it's active or not, so it has shapes like this and shows you where the bass drum is. Now you can either initialize some of these components by speech. So you're having some components initialized with speech, maybe 20, maybe 30. If you're choosing too many components, it doesn't matter because further components are left empty if there aren't as many in the signal. And then leave maybe one or two free, and the one or two free components can then model the noise, which is not speech in the signal. And then you're getting the activations, and you can see when is the noise active, when is the speech active, and you can recompose or resynthesize by keeping the phase from the original signal, these signals. So here's an example for that.
Now I see places and faces and things you ain't never thought about thinking. If you ain't peeped, then you must be drinking and smoking, pretending that you're looking, but...
So you see it's heavily noisy, and it's correlated noise in a way because it's music and it's following, at least in the same rhythm or something like this, the singer.
You're broken. Let me get you open. Now, little Timmy.
Now we initialize with speech. Then we know in which components the speech is, and then only add up the speech components.
Now I see places and faces, you things you ain't never thought about thinking. If you ain't peeped, then you must be drinking and smoking, pretending that you're looking, but...
And the rest, which has all been excluded. Now if we don't initialize, we don't know what's inside these component spectra. So we need a classification. We get blindly decomposed spectra, and we need to classify is it speech or not speech. And then we put again those together which are speech labeled. And here's an example for that.
Do you have the time to listen to me whine about nothing?
So we put together all those classified as voice.
Do you have the time to listen to me whine?
And all the remaining ones.
Do you have the time to listen to me whine?
And of course there are some artifacts in both of these. And we will later on also see a way to use this as a feature extraction where we initialize these components. Think of you're initializing these with different types of phonemes. And then you get the activations. And then, of course, these activations could be used as features because they indicate which phoneme is more likely to be present at which moment in time. Yeah. Now, what is the perfect strategy to decompose this? The answer is there is no perfect one. It's not unique. So each different strategy leads to different results that can be differing in perceptual quality, that can be differing in number of iterations needed. And there are several strategies for decomposition. I only wanted to highlight this together with the long short-term memory recurrent neural networks, simply because it gave us the best results in the recent past. For example, we had the best MIREX challenge results for tempo and onset detection with the neural networks that could exploit long-term dependencies. We're currently having the best chime challenge results for keyword detection in noise by combining these two. So we're first separating the voice from the noise and then using the long short-term memory networks to model contextual noise, to model temporal context, which is particularly suited in noisy settings, because if you're having non-stationary events, you can still exploit what is left and right from that. And acoustic robustness, only a very short excursus. We have the chain of processing, so from capturing, pre-processing, feature extraction, and so on, to the classification, if you remember from the beginning. And we have different points where we can do something in the pre-processing and feature extraction enhancement, either of the speech itself, as we've just seen, or of the features. So we can use feature enhancement strategies. Then we can introduce features suited to the specific noise or reverberation situation. We can adapt the models and the feature space, so we can select features in the noise and find a feature set that is better suited for clean speech, one that is better suited for noisy speech, or adapt, of course, the models and do whatever matched, mismatched, and multi-condition sort of learning. Also adapt the language model. And then we can choose other model architectures like the long short-term memory networks that can deal with non-stationary noise events by having some stored context. There's a number of well-known techniques from the speech recognition domain for enhancement of features, for example, histogram equalization, unsupervised spectral subtraction, and so on. But hardly any of these are used so far in this paralinguistic domain. So there is a lot of expertise needed on transferring from the speech recognition domain to the paralinguistic domain. There are only a few examples of papers for noise. This is, for example, different emotion databases. And you see clean speech, for example, the Berlin very easy data set in terms of accuracies that you can reach 7 classes, some 87% in clean case. And in minus 10 dB, so meaning the noise being considerably louder than the speech, you still get 67% accuracy. This is a speech recognizer's dream. So apparently these paralinguistic tasks are not as much impacted by noise as speech recognition, for example, would be. There are several explanations for that. One is you're only having 7 classes, not 100,000 words maybe. The other explanation is that you're even, in particular for the non-stationary events, you're having several frames of audio which are not corrupted, maybe, and only some that are corrupted. So maybe you can benefit from that. And here is, for example, emotion recognition in car noise and different adaptation strategies: no adaptation, speaker adaptation, noise adaptation, meaning matched condition learning, and matched condition learning plus selecting the right feature set for the noise. And if you adapt the model to the acoustic condition and you select the right features for the noise, you can restore things perfectly. So in other words, there haven't been much papers about using HEQ, SLDS, and so on, but maybe it's simply also owing to the fact that it's not as much required, because comparably simple strategies can help to recover things very neatly. Now another issue is reverberation. So these are different room impulse responses. So they have rather long echo or a T60 time, or rather very short. So the room impulse response you get, of course, by making an impulse like clapping or blasting an air balloon, and then you measure the impulse response. And this is, I think, one of the only studies at all in this field to measure the influence of different room impulse responses from a van to living room to a chapel. And there's quite a downgrade going from a very small room to a larger room for different feature types. So it's per feature type, the analysis here. But the room impulse response, of course, does have an influence as well on these tasks. Yes?
Is this study published?
Yes. It's the, what is the, it's in the International Journal for Speech Technology. It's the Springer Journal. And Again, very simple matching strategies, matched conditional learning, matching the feature space, and things are recovered quite well. So, well, here you would have to compare these two bars always. But in any case, matching already does the job. So you don't even need to predict the room and pulse response or more elaborate things to get very good results in such a condition. But of course, it will be very interesting to see this for other states and traits, and it will be very interesting to see if you can do better than just matching feature space and multi-conditional learning. Then, of course, you also have audiovisual recognition of speaker states and traits. This is just one example in different noise, Babel noise, street noise, office space. With audio alone in SNR from 20 to 0 down, and audio plus video from facial features. And of course, you can also recover a little bit by adding further modalities. All right, any questions on the acoustic side up to this point? No? All right, then let's go into the linguistic part. So we looked at how something is being said, and now we want to look at what is being said. And first of all, you will need to capture the text. So either it's written text, well, sounds easy, but still you have to do something to cover for different spelling variations, misspelling, to chunk into whatever units of analysis. Or it's a spoken text. Then, of course, you have to deal with speech recognition, and speech recognition can be challenging because it's influenced by the state or trait, and we'll have a look at the impact of emotion, for example, on speech. Obviously, there is impact if you're drunk on speech recognition. There's often little expertise on the influence of these different states and traits on speech recognition. Mostly covered is emotion, probably, but for the other states and traits, we don't know what is happening if you're tired and so on. But in any case, it will impact very likely. And then you will have to do some tokenization where you decide for the unit of analysis. Is it one word per one word? Is it an n-gram of 2 words, consecutive words, or 3? Is it character n-grams maybe, so only a sequence of phonemes or characters? Then you will have to think of the words that are carrying information of interest. You can think that, or imagine that not all words will be of interest, like some function words might not be of interest, whereas some swear words would be of higher interest in the context of emotion recognition. And then you need to stem, meaning that you reduce the word to its word stem to cover for different conjugations or flexions of the word, and can consider different retagging of the words. So let's look at this in more detail. So first of all, the usual representation forms that are popular in this field are n-grams. So we're not looking at a single word, but at a series of n consecutive words. And then look at the probability of this sequence of words to speak for the class of interest. So for example, we count how often does I hate you appear in the context of anger, how often does it appear in the context of joy, and from that derive the overall probability of the overall sequence. There are different ways to calculate these, and due to sparseness of data, in particular for such linguistic considerations, you need loads of data. So with a database of 30 minutes of speech, you will hardly be able to train something meaningful that generalizes well. You usually mostly find unigrams in the literature. I think the largest you would usually find is trigrams. And of course, these larger n-gram sizes appear less frequently in the corpus than do the unigrams. Now, another very popular representation of linguistic information is the back of words. So what happens there, every word in your test training corpus is taken to the vocabulary as a feature. So I hate you makes I a feature, hate a feature, and you a feature. And then in your test instance, you count how many I's do I have, how many hates do I have, how many yous do I have. And you have a very large features vector, of course, by that. Because if you imagine every word, maybe it's 60,000 words in your corpus, maybe in a spontaneous speech corpus only 2,000, but still it gives you 2,000 feature dimensions, of which many, many will be 0, of course, because in a test phrase there are maybe 5 words, maybe 7, meaning that from the 2,000, almost 2,000 remain 0 and only 7 are different than 0. Now the back of words do not model contextual dependencies, so you could make backs of n-grams and have I hate you as a feature. Now you can imagine how that blows up the feature space, because if I model every n-gram that could occur, I have a very, very large feature space. And that makes stemming and stopping very much needed. You can also retag, as I said previously, I hate you as whatever noun, verb, noun or something like this, or by semantics, and then have different features. One is noun, verb, adjective, or one is noun, verb, n-gram, and then the original features, and combine these in the feature space. You can do all sorts of transformations for these features. You can either only count binary, is the word there in the test phrase or not. You can count how often does it appear. You can normalize it to how often did it appear in the training corpus, how long was my test sequence. You can use the logarithm or not. So again, you can do many, many explorations in the feature space, how to optimally craft your feature from that. There are some specific solutions like subsequence kernels. So there are support vector machine kernels that can handle strings, where you have no feature calculation, at least no explicit feature calculation, and they can handle non-contiguous string subsequences, but they were mostly reported to be very, very demanding in terms of computational effort and not giving you much more, or not more than the simple back of words. And an advantage of these is, particularly the back of words and back of n-grams, you can very easily integrate them with acoustic features in one vector, because you're having all your pitch mean, MFCC1 mean, together with how often does I occur, how often does hate occur. Another larger field is the field of open domain sentiment analysis. There are many, many resources on the net, like ConceptNet, WordNet, General Inquirer, that allow you to have something not data learned, provide you features for text analysis. So far this has mostly, if not exclusively, been used for affective analysis, emotion analysis. And you can look up in these dictionaries how related is the word hate to the word anger, or how related is hate to the word joy, for example. Or in some of these dictionaries you can directly look up the valence score for hate, the valence score for joy, and so on. So this is the type of information you would get from these resources, but why not think of considering these resources also in other contexts, be it intoxication, be it sleepiness, be it whatever, personality assessment. Now here is one example for linguistic analysis. As said, they require a lot of data, so usually with the smaller corpora, it's not very meaningful what you get. So we used movie theoretics, like in the sentiment analysis field, where you, or opinion mining field, where you only want to know is it positive or negative. So binary assessment is a review in favor or not. And here we downloaded the largest movie theoretic corpus to date, and I can recommend, if you're interested in that, to use it. Metatheoretic provides a collection of reviews that appeared in different magazines and maps it all to a 0 to 100% score range, which is not very evenly distributed, because some magazines only have 3 stars ratings, maybe some have 10-star ratings, so they attach 7 out of 10 for a movie. So this gives a not very well distributed score, but it provides 100,000 reviews, if you wish for, in positive, negative, and neutral. And we divided these by year of occurrence of the movie, so the results are all movie independent, and now we have millions of words to train on and to analyze. Metatheoretic only considers the key excerpt of a review, so it does not consider the whole review. It provides also the whole, but it provides this key statement. And for the best movie of all time, The Godfather, I'm sure you probably mostly know it, the best review would be, it put a smile on my face that never left for 117 minutes. So this could be such a short phrase, and from this phrase we want to derive, is it positive or negative? The worst review would say, if it's all supposed to be in fun, why does it feel so much like an insult? And a mid-range review would be, although some of its parts are brilliantly executed and played by a terrific cast, the result is scattered, over-amplified, and unsatisfying. Okay, so these are the types of statements. Just like in a speech dialogue, you are having rather such sorted statements, which we want to have the sentiment derived from. Now here we're looking at different n-gram lengths from 1 to 1, so looking at words in isolation, 1 to 2, couples of words, triples of words, and so on. And the best is triples of words. For this very large corpus, you can train meaningful triplets of words, but nothing larger than that. And actually, it's back off n-grams, meaning that we not only consider the triplets, but single words plus duples plus triples. Here later on, we're not backing off, so we're only using duples or only triples, and that is considered verse. So the best idea is to use 1 to 3 word compounds, but you can also see that the difference is not very, very large, even for such a large corpus. So probably you can simply look at words in isolation, which was a surprise to us. Then we look at the different feature representations. I said you can simply count the number of occurrences of a word in the test phrase. You can normalize it to the length of the test phrase, use the logarithm, normalize it to the occurrence in the training set, and so on. You can use many different representations, and almost nothing happens. So, meaning that you can simply use single words and simply count if they're in the test phrase or not, and probably you're doing a good job already. And then we compared it to the open domain features. So we're looking up in general acquirer, effective word lists, and so on. How distant is the word hate from anger? How distant is it from joy? But we're not training with domain data. This is the back of n-grams, which was the best for the data-driven learning with support vector machines compared to the online knowledge sources. And you can see that the accuracy is heavily downgraded for the online knowledge sources. Some, almost 10% worse. But then again, imagine that you never needed training material. You needed nothing to be done, and you're completely domain independent. So Metacritic also provides music reviews, game reviews. Maybe you can do a way better job. We didn't test it so far, but maybe you can do a better job by using that rather than training on movie critics and testing on music critics than simply using something that has never been trained. You can also combine these two. One obvious way to combine these two is to use the online knowledge sources to recover out-of-vocabulary events, meaning if you have never seen a word in the training material, you can look it up with the general knowledge sources and add information on this word, or you can substitute it by a synonym. These are very well suited, the online knowledge sources, to find synonyms and substitute as long as needed to have only words which occur in the vocabulary. And by that, recover almost all of these. Okay, so the next problem is to deal with speech and not with text. And I said, what are the problems of recognizing speech given that the speech is under the influence of a state or trait? We looked at emotion here, and again at the corpus from the 2009 Emotion Challenge. The children, if you remember, playing with the Aibo dog. And we looked at which data is best for testing and which is best for training. Now, if I asked you which data is best or easiest to be recognized, you would probably say neutral speech. Or at least that's what we said. And in fact, it wasn't. We had better results on emphatic speech and on angry speech than on neutral speech. And we explained it because neutral speech is very spontaneous, maybe fast, and less pronounced, whereas the emphatic speech is more pronounced. So here are examples of those.
Okay, jetzt wieder aufstehen.
So this is neutral.
Okay, jetzt wieder aufstehen.
This is emphatic.
Jetzt nach links.
So you can hear that they are very in isolation, the words, with pauses and very clearly articulated. And this is anger.
Aibo, bleib stehen!
So it's partly having some other effects, but still it's maybe better articulated. And the second surprise was which is best for training. Maybe it's not as much as a surprise. The best to train is simply to use neutral speech, which is good news, because that's what speech recognizers are usually trained on anyways. Second best was emphatic. than angry and than Mother Reese. We wanted to have an explanation for that and did a Salmon transformation. A Salmon transformation is a cluster-preserving transformation from a higher dimensional space to a low dimensional space. In our case, to a two-dimensional space. So this is the MFCC space and or the spectral feature band space. And each dot here is one child of the 51 in one emotion, meaning the different colors are the 4 different emotions, and each spot here is one child averaged over the different emotions. Now we can visualize the main variances by these ellipsoids and see that in the center of it is the neutral speech. This is the green speech. And the other speeches, other emotions are dispersed around this center versus Mother Reese speech, which is clearly outside of the center. Meaning that in the spectral space or in the capsular space, emotional speech is around the neutral speech, which is one explanation why neutral speech could be best for training, because it best covers independent cases. The other explanation is the IBO corpus was annotated on a word level, per word level, and the turn levels are based on the per word levels. Now, if you look at the number of neutral words in a neutral sentence, you will find that only 95% are neutral, meaning that even if some words are not neutral, if the majority of words is neutral, it's mapped as neutral. If you're looking at an angry sentence, there are still 30% neutral words inside, and emphatic even 56%. How come? Imagine I'm saying a sentence like Saturday, Sunday, Monday. You see, I'm not angry or negative or whatever throughout the sentence, but I'm focusing on one word. Still, you would say when I say Saturday, Sunday, Monday, that I'm on a turn basis negative. So in other words, given that many words are still neutral, even if the turn is labeled as not neutral, training on neutral speech is a good idea. Now, can we or should we adapt models to the type of emotional speech that we're listening to? In other words, should we recognize the emotion first rather than using a neutral model and then adapt the models and use an angry model if recognizing angry speech or not? And again, to cut a long story short, these bullets here indicate significance levels going from 0.05 to 0.01 and higher significant and more significant. We had an adaptation of a neutral ASR engine or a neutral versus emotional ASR engine, meaning that we only train the engine on this one emotion, try to recognize the emotion, and then use the anger ASR engine, or that we use a neutral trained but then adapted ASR engine. And both adapting the acoustic model and the language model highly significantly helps to do a better job in speech recognition of emotional speech. So in other words, adapt the acoustic model, seems obvious, but even adapt the language model to the emotional speech and you're better off in terms of speech recognition rate. But what about the impact of false recognitions on the emotion recognition or a speaker state and trait analysis? Here we're going down with the word accuracy from right to left. Still the same corpus, the VIBO corpus of the children playing with the pet robot. Simply by reducing the beam width of the search for the best hypothesis, we can artificially downgrade the speech recognizer's accuracy, and upwards we see the average recall for the emotion recognition for different variants, matched and mismatched training, and different types of accuracy, weighted and unweighted. But let's not care about it, let's only care about this pattern going down. Meaning that we can have a surprisingly low speech recognition accuracy. The best we had was around 85% on this corpus. But if you downgraded it to 50% almost, it almost hasn't much of an impact on the accuracy. And then at some point later on, obviously it goes down. And now the question is, why can I have such corrupted speech recognition and still recognize emotion so well? Well, this is a two-class task. It's negative or not, and you can imagine as long as words are not substituted that inverse the polarity of the emotion, it doesn't matter. As long as words are deleted that don't carry the information on the emotion, it doesn't matter, sort of. So if you think that in an angry or negative sentence there are still 30% neutral words, maybe it deletes the neutral, acoustically neutral words, and I still get the negative touch of it, linguistically, sorry, neutral words. And as long as it doesn't insert something from the other polarity, it doesn't make things worse. So in other words, we're dependent on the speech recognizer's accuracy, obviously, but it's not as much of an influence as you would think or as you would be afraid of. Still, there is hardly anything exploiting speech recognizer confidences for the recognition of speaker states and traits. So if you want to use linguistic information, please write a paper on showing how can we best integrate acoustic confidences from the speech recognizer, because this is hardly exploited so far. All right, any more questions on the linguistic side? No. Then let's move on to the non-linguistics. This is very example-driven. This is the audiovisual interest corpus that you had seen for the interest sub-challenge, and as an example for data collection, we had labeled breathing, consent, hesitation, and laughter. So breathing is obvious, something like this. Consent is mm-hms. Hesitation is hms, or something like this. And laughter, well, it's laughter. And we try to recognize these. You've seen results already for that with audiovisual recognition. And usually the papers that report results on these do this in isolation. So you're having the laughter and breathing clips, and you recognize these from each other, which is, of course, a significantly easier task than doing a detection of laughter in the continuous speech signal. So to give some numbers, you can get some 90% for these different types speech versus any of these events in isolation, but you only get 80% if you do a detection task where you really have to localize it yourself in the continuous speech. Now this is of interest for the speech recognition, because if you localize these events, you're ensuring that they are not substituted to words. It's also interesting for the analysis of speaker states and traits, because obviously if somebody's laughing a lot, you would assume him to be more joyful. Maybe if somebody's hesitating a lot, you would assume him to be more drunk. So you can see that they can be of interest for our scenario as well. On the IBO children corpus, we found 6% laughter roughly, so it's not too much but not too little, and had some 72% for speech, laughter, or both as a ternary problem. And I only want to look into this specific case in a little more detail. First highlighting which classes you could be coming up. So it's not only laughter or not laughter, but it's weak or strong laughter. And it's speech laughter or only laughter. You can have speech laughter with a strong laughter presence in the speech, or with a weak laughter presence. Then you can have voiced laughter or unvoiced laughter. And you can have no laughter, so only speech. So we're already having 6 classes of laughter with different distributions. So even somewhat evenly, the voiced laughters are less present than the voiced and unvoiced mixed ones, obviously, and less present than the unvoiced laughters, or the types of laughters were more present. But what is interesting is you can even exploit some context knowledge here, some temporal context knowledge. This is looking at syntactic positions in a clause. So how do laughters appear? Are they appearing in isolation? That is what happens most of the time. Are they appearing, so this is speech laughter, laughter, and total, but let's simply look at the bars for laughter at the beginning of the unit, at the end of the phrase, at the end of the clause, left edges and right edges and covering and so on and so forth. But what you see is you really get different a priori probabilities at different positions which are somewhat distinct, so you can expect the laughter rather at the end of a phrase or rather in isolation. And that makes you think maybe again of the long-short-term memory recurrent neural networks. So this is another example where a network could learn this contextual information and this contextual behavior, and maybe could even learn it a little bit by itself, such contextual dependencies. Then, looking at the different emotions, you can see that speech laughter is strong or weak. Both occur more frequently in joyful than in angry speech. No surprise, but it's sort of evidenced by data, so the emotion does have an influence. And you can also look at the position of laughter within a whole dialogue, not only on a turn-by-turn level. Of course, this is heavily influenced by your application, but if you're tailoring a laughter detection system, say for a specific type of call center dialogue, you will have this contextual limitation and you can use it. So here, for example, in the FAU IBO corpus, the laughter occurred mostly at the beginning of the overall dialogue, which seems to make sense because it's a social signal, and at the beginning maybe you're trying to sort of socialize. Later on, the children realize that it's a pet toy electronic robot that doesn't laugh back at them. Maybe they stopped to laugh at the robot. Maybe it was behaving so disobediently that they weren't thinking it's fun anymore. But maybe something similar is happening in a call center dialogue, where you're also at the beginning, well, laughing more and later on less. So you could even use prior probability adapted to the position over times. Yeah, now this is mostly some more accuracies to give you an impression for these different types. So for 3 classes, speech, laughter, laughter, and words, we had some 74% recognition rate for 6 classes. So all these weak, strong, voiced, voiced, unvoiced, and unvoiced laughter, some 55% recognition rate. Now this brings me back to what I had been talking about beforehand when we were talking about the non-negative matrix factorization. I said we could exploit the activations over time as feature information. If you imagine you're using these spectral components from the, so you're having your spectrogram over time from the speech signal, and then you decompose it into the spectral components and their activation over time. Now you could initialize these components with laughter, with psi, consent, or whatever sort of spectral prints, and you can use several prints to get characteristic components. So maybe not only one laughter component, but 5 different laughter components or 10, and then you're decomposing it into these spectral prints and the activations over time. But now you're having these initialized, and instead you're only computing the activation over time, and by that you're getting a probability, sort of pseudo probability, for laughter being present at time instant n, or consent being present at time instant n. So this is the principle. We're having some supervised non-negative matrix factorization. We have the samples per class to initialize these spectra. So we're having the spectra fixed, and we have the input signal and only compute the activations over time. Of course, we could leave an additional component free for free decomposition if it's neither laughter nor hesitation, or maybe even not speech. So we could even use 2 or more free components. And then we can look at the activation histogram, for example, for consent. So this is the instances of consent and the activation of consent at this time. You see, when consent is present, the activation still is often 0, which is bad. but it's very often not 0, whereas if we have a other non-constant instance, it's more or less always 0. So from this histogram, it already looks very good, and we were thinking if we can use this as a feature. So here, first of all, we're looking only at recognition of the of this type of information without an additional classifier. We only look which has the maximum activation in different types of components, 70, 90, or 100 components with different strategies, Euclidean distance or Hilbert-Leibel different distance. Anyway, it's around 80%, and we only use this type of feature, not even a real classifier, only finding the maximum. Now the question is, can we combine it with MFCC features? And the MFCCs give some 86, so above these roughly 80, but in combination with the activation features, it gives a 2.5% significant heap. And I've been mentioning the time challenge task where you had to recognize keywords and the noise, and I said we were using our long short-term recurrent neural networks to better model contextual information. I said we were using the non-negative matrix factorization to enhance the speech signal. Now this is the third thing that we had used. We used speech activation features from the non-negative matrix factorization as a third stream in the model, and had another significant improvement. So in other words, this is my current feature highlight, the activation features. Right, any more questions on the non-linguistic vocalizations? So let's go to the multi-stream and multitask fusion. Actually, it's mostly multi-stream fusion, what I'm discussing here. Who's working on multimodal integration? Several, not everybody. So I'm first boring those working on it by talking about early and late fusion, and then hopefully say something interesting by hybrid fusion. So in general, we have multimodal fusion here already. In fact, I've been discussing a lot with Louis-Philippe Morancy if this is multimodal or not. I say it's not, he says it is. And I'm talking about combining acoustic and linguistic information. To me, it's not multimodal because it's the same modality. We're looking at speech and we're looking at acoustics and linguistics, but others perceive it already as being multimodal. But in any case, it's a multi-stream fusion, and we already have the question, how do we best integrate the information? Now, the obvious problem in integrating this type of information is it's usually operating on different time levels, because we're having the acoustic information either on the per frame level, 100 frames per second, or on the suprasegmental level, maybe over a whole turn, but maybe only per word or per voice segments or something like this. On the other hand side, we have the linguistic analysis operating usually on a per turn or larger entity level, because as much as we can get is well, the more linguistic information we have, the better it is. So in early fusion or early feature level fusion, you simply put it all into one feature level. This would be the case where we put the back of words into the same feature vector as the mean pitch or whatever other acoustic feature is. We assume the same sample rate, require high computational power. The high dimensionality increases the numbers of parameters for the learning algorithm. So we would usually try to introduce some feature reduction like PCA or LDA. It requires large amounts of training, and we hardly have this from the same database because usually we have unimodal databases like speech emotion, visual emotion database. If you remember the text here, we had hundreds of thousands of movie reviews, but of course no acoustic feed for that. So usually this doesn't work if you're not having it in the same database, which is a downside. But as a bonus, you get the best results if the signals are highly correlated, and of course they should be. The linguistics should match the acoustics in the sense of being intoxicated or not, or being joyful or not, or being tired or not. And the recognition of one mode influences the other one. So the popular classification approaches, well, I mean, you could be using anything because you're integrating it into one feature vector. One interesting thing to mention here is the projection into a static vector by time series analysis. So if they are operating the two modalities on different time levels, you can use functional projection to get them on the same time level, and by that produce a static classification problem, which is a compromise to have it all handled by one classifier. Now the late fusion or late semantic fusion, in a strict definition, has an output per stream or modality as a recognition result. So for example, drunk or not drunk from the acoustics, drunk or not drunk from the linguistics or any other modality. In a less strict definition, you could be saying that you're also forwarding, so to say, confidences. So I'm 90% sure from the acoustic that it's drunk and 10% that it's not drunk, and so on and so forth. You can then model the signals separately, profit from good availability of unimodal data, from good expertise to model these individually. Be very fail-safe. If one modality drops out of it, you can still use the other ones. You have an easier scale-up. You don't need to retrain everything if you add a new modality, but you can just plug it in, so to say. But if the modalities are correlated, it should usually give you less good results than the early fusion. So how do you classify? Well, the simple approach is majority vote. You count how many streams or modalities speak for intoxicated, how many for not. You can have unification grammars, agent-based voting, finite state transducers, statistical methods. Most of all, you can train a classifier to learn whom to trust when, so to say. So maybe you trust the linguistics rather on joy versus not joy or anger, so on the valence side, and maybe you trust the acoustics more on the arousal side, because acoustics are very good to measure the arousal activity and not so good for valence. Now the hybrid fusion tries to combine these advantages, so to be flexible and also handle asynchrony, to exploit the mutual information as the early fusion does. And a number of popular classification approaches are asynchronous input-output HMMs that consider the shorter stream as output conditioned by the longer as input. Asynchronous HMMs, multidimensional DTW. This is an algorithm that we had introduced to synchronize the modalities with a very efficient way by a DTW, and later on you can use the synchronized streams in a normal HMM and meter classification. So, however, you will sparsely encounter hybrid fusion in the field of state and trait analysis so far. I hope to see more of that in the future. What is usually being used, in fact, is probably mostly late fusion, simply because it's very easy to combine linguistic analysis. Yes?
What do you mean by the meta fusion?
Actually, it's using all the confidences or scores from the different modalities and learns, yeah, as I said, whom to trust when, but based on intel from these scores. So, I mean, this is a matter of definition. You could call it a late fusion still. Some people define late fusion as only using the yes-no decisions. Yes, exactly. So it's not as hybrid as the synchronization and input-output HMMs. Yeah, and some of the linguistic feature analysis allow more or less for integration into an acoustic vector. So this is just one example again on the emotion corpus with the children. We had fused 5 different engines here: linguistic only, linguistic, dynamic acoustic modeling, static acoustic modeling, and so on. And each of them being below 70% and the late fusion by democratic vote, giving some 70%, then learning the fusion whom to trust when, got even worse results depending on the type of learning scheme, and then with the right learning scheme, better results. But here the picture is combining several different engines that really provide a different type or approach to modeling. Dynamic or static acoustic modeling or linguistic usually gives you a benefit, as shown by the fusion of the participants of the challenges. Apparently the strategy, how to fuse them, doesn't matter this much in a late fusion. A democratic vote usually gives very similar results to something fancy and elaborate, probably again simply owing to the data sparseness. So there is not much to learn, even that on top of learning the state and trade, whom to trust when. Okay, more questions on this part? No. Yes.
Yes, you talked about the learned fusion in the hybrid technique, but it's really you need more data to do this. If you had to learn classifiers, then learn another classifier to learn on the input of the late fusion classifier.
Sorry, say that again, please.
I'm gonna reformulate. Isn't it a problem to have to learn the fusion? Don't you need more data?
Yes.
Even more data?
Yeah. So ideally, I mean, you can do it on the same data, but ideally you would want to train it on independent data. And this is why I say, given the data sparseness, you probably don't get much of a gain in learning the best fusion scheme, because there's too little data to first learn on independent data, the individual engines, and then on other data, the optimal fusion scheme. But you could do it on the same data to learn the fusion scheme, only that you would expect it to be less meaningful.
Okay. Do you have an idea on how does it scale? How much more data do you need?
To be frank, not really.
Okay.
I mean, the simple answer is more is better. Probably you should have at least half the amount of data to learn this part than as compared to what you had used in the first place. But I really wouldn't be able to come up with a rule of thumb or good number here.
Okay, thanks.
Okay. So this brings us to application. And to a very short anecdote. When I started to work on speaker state and trait analysis in roughly 2000, I was sitting together in a room with as a young PhD student with a speech recognition expert, and he would always call what I had done esoterics with HMMs, the emotion recognition, and everybody would ask me, what is the application for this? So nobody could imagine, what do you need this for? So let me play a little game with you now and ask you, what applications do you see for this? And let's prove that it's not the year 2000. And it's more obvious what the applications are. Do we need this at all? We've been talking for 3.5 hours. Yes?
How often does, for instance, to know whether the user is engaged or is frustrated or whatever?
Yeah, exactly. What else?
Yesterday we had an interesting conversation with Alex Acero regarding these kind of things. He was
okay.
A little bit frustrated. He said that there were no much applications where emotion recognition could be applied to the best of his knowledge. So we had a deep discussion on this.
I see,
it could be
okay.
nice that that he could be here.
You said that from a commercially wide commercial applications point of view, so you have smaller impact applications like remediations, therapeutics for autistic people, people with social phobia, this kind of thing. There are some applications, but it's not as wide as a natural language recognition.
All right. So let's see what I have in mind. And I always feel like it's not 2000 anymore, but maybe I'm over enthusiastic, because I feel now that speech recognition is more and more available even on smartphones and somewhat working now. It's the next big thing to integrate more and more of this state and trait analysis simply because the human does it. And if we talk to each other, we constantly evaluate the emotion, the age, the gender, and we adapt our behavior to that. So my belief is that it's very, very needed, but it was already like this in 2000. I thought it's very, very needed. And here is a bunch of application areas. Maybe the most abstract first, that is encoding. If you think of encoding of speech, you can use linear prediction or something like this, and you can transmit in the GSM standard, for example, or even if you think of space communication, very limited parameter set, and maybe low-pass filter speech signal to have the excitation. In an even more dramatic encoding, you could only transmit the words and then resynthesize at the receiver's end. But something in between, of course, could be that you encode the emotion, the age, the gender, and everything, and maybe a short characteristic print from the audio to resynthesize very similar to what it has been spoken like, but at a very small bit rate. And in fact, there are some standards, like in the MPEG-4 standard, where you have the Ekman Big 6 emotions already standardized that could be a starting basis for this. Then we have analysis, editing, and synthesis. You could have a voice conversion, for example. Imagine you're talking to your boss, but you're really frustrated. You just don't want to sound like it, so you could have an online upgrade. Maybe you're at the Oktoberfest in Munich. You're completely drunk, and you get this really important call. You don't want to sound this drunk. So you could have it edited and resynthesized. Then, of course, media retrieval is a large field where you always have these highlight spottings in baseball games, soccer games, and so on. But you could think of other highlights that you want to retrieve based on speaker states and traits. Who knows, maybe label the age of speakers and so on, or the gender. Then we have natural interaction, and I want to show a particular example of that later on. But the natural interaction usually is what I just said. Human-to-human conversation is heavily based on taking into account the age of my conversational partner, the gender of my conversational partner, and all sorts of reacting to these laughter, sighs, and joy, and so on. So why not have a robot or computer adapt to that? Then we have monitoring, and in the coffee break there was an example of surveillance application where we want to monitor threats like aggressive behavior. But we can also think of customer monitoring, where we want to know when is a customer interested. So in a product presentation, when is somebody more or less interested? And then a particular field is coaching. For example, you could produce a software that teaches you how to give a good speech. So I should have used it before this talk today. And then I could have learned maybe to sound more like a convincing person or sound more like a leader or whatever. In fact, we had an article now on how to sound more convincing or more leader-like. So you can have all sorts of such states and traits for coaching. A particular one is interactive emotion games, and that brings me to some examples from our application. Just to give some more concrete examples, this is the European project I'm coordinating at the moment, the Autism Spectrum Condition Inclusion Project, where we have children play, autistic children play with a video game, and they love video games, which is why we think it's a good approach to have them play. And the video game teaches them how to show their emotion in the right way. So it's like a karaoke game for emotion. Imagine it plots some whatever pitch intonation contour and says to the children, in order to gain their points or to gain their collectibles, they have to sound more joyful, but it gives concrete advice how to sound more joyful, things like that. This is Robina, a robot that will guide you around a museum in Japan, and it takes into account your interest from our software. So if you're completely bored, it changes exhibit, and that sort of works to a certain extent. I'll have an example on numbers later on. So for example, if I had this software, it would maybe have a red light now, and I should skip the slide. So this is the idea. This is a camera as in surgical operations. If the surgeon, it's voice controlled, but if the surgeon is under stress, It uses different acoustic models and has fallback mechanisms. And these are the sensitive artificial listeners, and this is the example I want to show to you as a video clip. And this is the main project that has just terminated some months ago. And this is a completely automatically driven avatar that talks to you. It's a sort of a chat partner like Eliza, but 2010, so to say. So it's not text-based, but audiovisually based. Who knows this? Okay, many that don't know it, so it's still of interest. And the user is talking, and it's audiovisual input analysis, so emotion, laughter, and so on, social signal recognition from the audiovisual input, and fully automatic generation of audiovisual output. And this is a naive subject. At the end of the project, we had 144 naive in the sense that they didn't know the system, and they're not even technicians, but from the university in a broader range at QUB. They talk to this chatbot, and you can see how it takes into account all sorts of head nods and shakes, but also speech analysis in terms of interest and effective signals. And of course, very simple speech things as voice activity detection to barge in at the right moment, take initiative at the right moment, and so on and so forth. But let's listen to this example of fully automatic conversation.
Trying to kid.
You.
Well, I'm Spike. What's your problem?
I don't have a problem.
Is that so? Tell me about it.
Well, you know, nothing's going
I
terribly
suppose you
wrong.
really think you're something.
No, not really.
How can you believe that?
Quite easily. I'm not up myself, I'm not spoiled.
Well, I think you're wrong to be so pragmatic about it all.
Really? Well, you're not always right. I'm not always right. So. Yeah. I think you're too harsh. You have to sit back and just, you know.
Go for it.
Yeah, just try and chill, see the world
Yeah.
through less angry eyes. You're too
You've
angry.
got to show people who's boss.
Yeah, but that just causes conflict.
So?
Conflict's a bad thing.
Oh, you're so pragmatic.
I don't even know what that means.
Yeah.
Nah,
That's feeble.
sorry. Not everyone's as tough as you.
Yeah.
No. Some people just like to.
Okay, so you can see it works surprisingly well, and I think some subjects talked even for half an hour to this chatbot. Simply by barging in at the right moment, making the intentionally different or same patterns of head nods and shakes and whatever tilting, and take into account these effective signals, but not really what is being said. So there's a little bit of keyword spotting, but it doesn't really have a gist of what's being talked about. Now here are some commercial applications. Few made it to the market so far, but some exist, and most of them went off the market already again. But this is the laugh detector, for example, a software that helps you to analyze if your conversational partner on the phone is in love with you. So pretty much of a toy application. There is even a service in China, I've been told, by Jianhe Tao, that analyzes your conversation on the phone and then sends you an SMS how much affection the other partner has for you. And apparently this is a very popular service under teenagers. They're superstitious or like such things, and they like to get such emails and saying that the other one really likes them. And of course, there's also quite an ethical responsibility in this. You can imagine that these emails hardly ever say somebody totally dislikes you, but mostly say that the other one likes you. This is a video game for the Xbox Choose or Lies. I think it also exists for PC or other systems, and you can imagine the type of game. I don't know if it exists in English, but in Germany we would have flipped a bottle and the one that it points at is asks some embarrassing question, and then the video game would judge if it was correct or not by the acoustics. Doesn't apparently work very well, but still it's fun and entertaining, and it makes people, well, talk about embarrassing things. So this is the handy thruster. I even got me one of those. I think it's completely off the market. That was one of the first hardware devices that was intended to recognize the level of stress, so if you're under stress or not, and again, truthfulness. So you could plug this into the audio out from your telephone, and while you're talking to somebody, it would show this, or you could use it here and ask somebody embarrassing questions. This is the Y-Cry, a device for young parents that tells young parents whether their baby is tired or hungry or happy or not. So it's aiming at quite a broader range of these speaker states and traits. We don't have hungry or not recognition so far. They have it in the product. And then some, well, other toys like magic flowers and teddy bears and stuff that react to your emotion. All right. Yeah, and I already mentioned ethical aspects, and ethical aspects are of interest not only in the product design, but of course also in the data collection. So which states and traits will be recognized can be connected to quite some ethical aspects. Also, if you want to free the data, of course, you don't want to have real lies distributed of yourself to a broader research community, maybe also not your drunk speech. So very often this is quite difficult. So the question is always who can access the recognition results and what use is made, and usually the agreements have different levels of for the different people the data is collected from to allow for usage for analysis, but not for using this in an audio demonstration in a public, or not using the images of the persons in journals and so on and so forth. Then, as for privacy and ethical constraints, Picard said, users appreciate being presented with a contract explaining how the system processes their affect, and significant difference are there in project use of system, comfort level, how they perceive their privacy being affected, and certainty in responses. So in other words, when inviting users to such a study, you better do a good job in explaining to them how the data will be used and offer them different levels of usage. Now, as for application, we've seen many results that are way below 100%. So the question arises, how can we best integrate this in a system context? One example was that we look at not only one instance, but try to make more sense if we have more speech available. But independent of that, confidences are very important, so that you not only attach he's drunk, or not only provide he's drunk or she is not drunk, but attach a confidence measure to this. And ideally, such a confidence measure should not only be the distance from the hyperplane from the support vector machine or something like this, but something more independent and more meaningful than that. And this is a almost black spot in the literature for the field. There are practically almost no papers dealing with confidence measurement. This is a surprise to me, because I think it's very much needed to craft more meaningful systems. So this is looking at the V-IBO emotion corpus of the children again. It's a very, well, difficult to interpret plot, but I'll tell what it is. We think of, given that we have several raters and we have some tasks being highly subjective, what we can try to use as a recognition target is not only the intoxication, the sleepiness, the emotion, but how many raters do agree on this. So independent whether somebody is sleepy or not, we train simply how many raters agreed on it. So that as an output, we sort of get the how reliable or how much would humans agree on this as an information. And in this study, we had 5 annotators, and the mean linear error by predicting the rater agreement was 0.2, meaning simply we could predict with a mean linear error of 1 rater how many out of 5 raters would have agreed, independent what the emotion is, we could have predicted, okay, 4 labels would have agreed on this. So this is one way to provide additional information and say it's a very prototypical anger or joy because humans would have very much agreed on this. Another way that we have as a peculiarity a little bit is the different representation forms. For example, for emotion, I said we can map emotions to valence and arousal or dominance. We can train on several databases. Even if these databases have completely different emotions or emotion number, we can all map them to arousal and valence, for example. The same holds for personality to a certain extent, and see how many different database-trained classifiers would agree in a more coarse representation of the problem on it. So maybe we're predicting really anger versus boredom versus many, many different emotions, but we're only getting an estimate from other data. How reliable or how reasonable is this is all in sort of arousal, valence, dominance representation. So in short, there are many chances here to exploit the peculiarities of the field to compute confidence measures, which are hardly exploited because there are no works dealing with confidences. I think it's simply that now that we're turning into the phase where this is all becoming applications in real life, that we're starting to be encountered with such questions. Another question in an online system or application is the processing time or the gating. Gating means from the beginning or from the speech onset, how much time do I need to predict the state or trait correctly? How much speech material will I need? This very messy plot here is looking at different feature types, MFCCs, pitch, and so on, from the speech onset for emotion recognition. Where you have some 60%, it's a cinema corpus you probably wouldn't know, but it doesn't really matter. What you're seeing is that after 1 second of speech, there is sort of saturation for most of the features here. So this is emotion recognition, and we measured for this data that we need 1 second of speech. And you can imagine this is very important in the agent you've just seen, this chatbot agent. Why? Because it has to prepare multimodal output. It has to prepare the facial animation. It has to prepare what is going to be said. It has even to synthesize speech, acoustic realization of speech. And it has to prepare all that. It has to prepare this for negative emotion. It has to prepare it for positive emotion. And the sooner we know while somebody is speaking a first estimate, well, the better we can prepare for the final result. It's just like if you ask your boss for a raise for your income or your salary, you're probably doing this throughout all of the discussion. You're always listening carefully and preparing different alternatives while he's still speaking. And then at some point when he finishes, you have to fire. You have to say something. So this is 1 second for emotion. We don't have no clue for intoxication and so on. We will need to have many more insight into those other traits and states. Now, together with confidences, something that is needed in my eyes to turn state and trait analysis into a huge success is distribution. We've seen this for speech recognition recently. Working on speech recognition for, I don't know, 13 years, I think, or 14 years. I've never used a speech recognizer myself. And I think it's true for most people working on speech recognition. It has changed very, very recently that I started to use a speech recognizer when using the smartphone and trying to find things on the internet for 2 reasons. First of all, you have a very bad keyboard simulation, and it's really painful to enter keywords. And then all of a sudden, it worked. I was really surprised what keywords you can speak, and it really finds them instantly. And I was wondering, what is the secret behind it? I think one of the major influence factors is also the distributed speech recognition paradigm, and in combination with the semi-supervised learning, meaning that by everybody providing his speech to the server, we can collect a lot of speech material, and by their choice in the end, if they choose the keyword in which they choose, we can have a good semi-supervised learning with a little bit of evidence from the application what speech was there. So we can collect masses of data, and I talked to Mike Cohn from Google about this, and he said as a rule of thumb, they need 10 times as much data, unlabeled data, to have the same heap in or gain in accuracy as if they had labeled data. And that is very interesting because if we have a server-based application, we can, of course, easily collect this 10 times more data. So we really started to go look into distributed recognition for emotion first and for other speaker states and traits next, to make it available on the smartphone, to make all these applications, be it fun applications, be it more serious applications, and profit from collecting a lot of data from the users. So not everybody has to update his own software with only their own speech, but we can centralize, update things. But there is another reason why we would want to have distributed recognition and with specific methods, and that is privacy. If you remember what we've been talking about, the ethics, you don't want your drunk speech or whatever speech collected on a central server somewhere where you don't know what is being made of that. So we do need to think of some good encoding of the information so that it cannot be restored. Now, if you look at experience from the ASR domain, how is distributed speech recognition handled, you can do vector quantization, and you can do the front-end bit on the speech processing device on the smartphone. So you're extracting the features, and you're transmitting some compressed representation of that to the server in order to save bandwidth. On the server, you're doing the processing in terms of the back-end processing, the machine learning part, and you send back the recognition result. Then on the server, you can learn your models, you can adapt on a daily basis with new and new speech coming in. But the question is, what is a good representation from the feature side? And here you can have an audio, which of course would be a bad representation because everything is in there.
Oh, it's a good price. Oh, it's a good price. Oh, it's a good price.
And if I sent or submitted all MFCCs, it would of course be a massive reduction in bandwidth already, but I can reconstruct from the MFCCs that a speech recognizer would need, like this.
Oh, it's a good price. Oh, it's a good price.
So clearly you can understand what is being said. Of course you should. I mean, after all, the speech recognizer recognizes speech from that. Meaning that in our case, maybe this is not sufficient or too much still. Because if I'm angry and I say swear words, you could still reconstruct that. And if you imagine we need this much more feature information, we need pitch, we need energy. If you're having pitch on top of MFCCs, you can, of course, resynthesize even better. And the more information you're having, the more it will sound like the original. So we think we can use these suprasegmental features, only the means, the statistics. You will hardly have a chance to synthesize what was being said from such statistical analysis over a longer segment of speech. And on top of that, we can look at the ETSI standard for the client side. So we do the signal pre-processing, feature extraction, then do some feature compression, like vector quantization, and then do some bitstream formatting. On the server side, we do the bitstream decoding, the feature decompression, and then the recognition. In our case, in the example, emotion recognition. Now you can have your training feature vectors, and you can use subsets of the features to be handled individually. Why? Because some of these features are MFCCs, some of these features are pitch, and maybe it's not good to make one codebook entry from a large variety of features, but it's better to use portions of the feature vector, and then do some clustering, meaning that you see, instead of having the original feature vector with its original values, you only look for 64 similar feature vectors and see which of the 64s is closest to the one that I'm having at this moment. Now, this means that you only have to submit to the server a number from 1 to 64, for example, if you only use 64 different code words. And then you can choose how many different sub-feature vectors sequences to encode individually. You can choose the code word length, and you can choose how many code word entries you have in your system, and then transmit, instead of the original feature vector, only these numbers. So it's feature vector number 128 for the MFCC part, 67 for the pitch part, and so on and so forth. So you have a huge gain in size compression. So this is looking at again, the IBO emotion corpus with the children, the baseline for negative versus idle from the challenge, some almost 68%. And now we're looking at different code word lengths, 3-bit up to 11 bits, and different numbers of code words. So for example, 8, 16, 32, 128 representative feature vectors. And you can see with 9-bit and 32 sub-vectors, we're very, very close to the baseline. So at a huge compression rate, so to say. And of course, nobody can ever recover what has been said from such a compressed representation. Okay, there are some other results for different code word lengths and bit sizes, but I think the principle is clear. We're not transmitting the original feature vector, but we're using we're determining the most similar feature vector from a number of limited feature vectors, and we do this per feature subset. All right, then if you turn things into an application, we want to encode the information so that it can be used by an application. And in the W3C, Mark Schröder initiated an effort to turn this into a real standard recommended from the World Wide Web Consortium. And I was part of the experts that tried to craft this standard, and which now turned into a working draft recommendation. There are other ones from the Humane Association, and some standards which are already W3C standards that contain for some speaker states and traits some labels. But we can look at this example from the W3C emotion markup language. There is an emotion core that describes the emotion-related phenomenon, but also other representation forms. Intensity regulation, so do I show my emotion or do I regulate it, temporal aspects. Then meta information like confidence levels or the modality, and external links to media somewhere in the web or on a file server, things like that. Global metadata, and so on and so forth. But to give a more concrete example, this would be emotion markup language for a system output. It says emotion at the beginning and end. Then says the category set, because everybody uses his own set, maybe joy and anger, maybe surprise and something else. Once this is specified, names the emotion, and then says the intensity of this emotion for a sequence of different samples or consecutive samples. So in other words, what you're doing is you're describing this in a well standardized way, and this will be needed for other states and traits to allow for easier commercial exploitation in applications. We even made a recommendation in the SACES working group, for the feature encoding. So before we had OpenSmile and OpenEar, we had pooled features, acoustic features from 7 different sites all over the world, and we wanted to select features not only extracted at one site, but from several sites. And for that made a feature encoding standard that encodes all sorts of information, the quality of the feature, linguistic features, acoustic features, the context used for computation, is it only one frame or is it using neighbor information, the context for functionals, context for normalization, blah, blah, blah. So many, many very highly specified descriptions that describe your feature at hand. And maybe you could be interested in this standard if you want to compare your features. Now, this is just one application design example. We're having the Semane chatbots here again, these virtual agents, and in the project we had feature extractors extract the features, write it to a whiteboard architecture where everybody can via TCP/IP communication read from, and then we have different analyzers. One is for speech recognition, one is for interest recognition, one is for emotion recognition. So in other words, we're having a centralized architecture where all audio features are extracted only once, rather than every engine extracting its own audio features. And every analyzer can read from this feature pool. Then they all write to another whiteboard their user state. So here could be the words, here could be the emotion and so on. And then they can read from this and also benefit from what other analyzers have to say about the current speech. And they can get some dialogue state information to reason from that as well. All right, any questions on applications and system integration? No? So here is the 10 trends part. And the 10 trends part starts with me asking you, what are the 10 trends? Anybody, any opinion? What do you consider as hot topic? Or what would you have observed if you're working in this field to be changing recently? It's good that you're having difficulties at it, because so had I.
I didn't see any mention of performance across languages, for instance. Should we study that if taking models from German would be usable in other languages like English or Spanish?
Yeah. So you're asking for cross-lingual analysis and evaluation of cross-lingual reusage or reusability, and how to best do that. If a system has never been trained in Farsi, how can I use my Bavarian accent trained system to transfer it to this? Yeah. Yeah, that's absolutely true. This is very needed. It's sort of a trend. And of course, it's a huge data sparseness issue because we have hardly resources in one language, let alone in several different languages, under the same conditions, so that we could compare the influence of language and start to learn. But it's absolutely a very well-needed point. It's even one of these here. Other ideas? All right, so I'll start with what I had gathered. It's not at all straightforward. It's just a bunch of things. It's not nearly in a unique order, or it's number one is not necessarily number one. It's simply what I came up with, and it's a bit of repetition, partly what we have seen. Number one to me is more tasks. Some years ago, we only did emotion recognition, and now we're doing, well, speaker height, weight, maybe soon eating condition or not. Who knows what's next. But in any case, there are more and more tasks coming up. And one example of a funny task I wanted to highlight as an example beyond the ones we've seen is we did a study on intimacy. We had mothers talk to their own children, to children not being their own children, and we had non-mothers at the same age talking to children. And believe it or not, we could discriminate way above chance level if a mother is talking to her child, to a child which is not her own, or to a grown-up. But we could even discriminate if a mother or non-mother is talking to a child. So you wouldn't believe what sort of problems you can come up with. And usually you're getting these typical numbers for two-class problems in the 70s that we've seen for all these intoxication and sleepiness and so on tasks. Some are even up to 80% maybe, like personality conscientiousness, if you remember. But all these things, if you think a man or a human can do it, somehow seem to work also with similar approaches like we've seen today for a machine-trained system. And often it can benefit from way more expertise, not expertise, but data than a human would usually have, because how often are you really looking at mothers talking to, well, their own children versus non-mothers talking to foreign children and so on and so forth, or drunk people versus not drunk people. Number two is more continuous modeling. In emotion recognition, almost everybody worked on the big 6 or other discrete classes of emotions, but lately we're seeing more and more of these arousal, valence, dominance schemes, which we're also highlighting in the audiovisual emotion challenges. But also for other problems like intoxication. Maybe you don't want to know above or below 0.5 per mil, but maybe you really want to estimate the per mil number. And more papers try to estimate the height in centimeters and things like this in a real continuum. Next one is more in cross data. So we're having very, very few databases at the beginning. For some of these tasks, we're now having the luxury to have 9 or 10 databases available, which are somewhat comparable, even like in emotion recognition. And this allowed also to do cross-corpus studies. Usually, of course, what we're seeing is that cross-corpus analysis is way worse than within corpus analysis. But then again, we believe that a real system is faced with cross-corpus. Imagine a multimedia retrieval system that has very, very different acoustic conditions and very, very different speakers and, well, conditions, in short. So we're starting to learn and gain more insight in cross-corpus results. There's also an increase in number of speakers and raters in these databases visible, because if you want to do a paper that interests people in terms of reliable emotion rating or likability rating, there are many databases that have 2 or 4 labelers already, but maybe you can come up with something that has even 30 or more duration of databases, but also cross-corpus feature selection to have a more general view on features. Then also usage. More databases are used per paper. In older papers, you will find 1 database. Nowadays, it's more and more common habit to use 2 or 3 databases to make a statement. And then, just verify if this trend is particular for true for 1 database or not. Okay, this is some example of cross-corpus feature selection. So far, there is not much proof for specific features holding independently of the database. So as soon as you go down to these very specialized features, it's really mostly true for 1 database in particular. Now, number 4 is more features and engines. You've already seen more features in this table, if you remember. So in the challenges, we had more and more features. We're somewhat moderate. There are even papers reporting 30,000 features and more. And at some point, you can ask yourself, are you producing more features than there have been data points? It definitely is a trend with an upper end. But still, it seems to be a trend to use more. At the other end, or on the other side, of course, there are still expert-crafted features, and there are still many papers trying to have very specifically tailored with a lot of expertise, hand-crafted features, and they're often proud to show that with 2-3 expert features, they can compete with your 6,000 brute force features. So it's a sort of two-sided trend. Then we have number 5, more linguistics and non-linguistics. There has been a very independent evolution of the field of sentiment analysis and opinion mining. And it's some workshops we organized at the LREC every year. We were really surprised how these communities coexisted until recently, meaning the people virtually didn't even know each other, and that there is a whole community dealing with text-based processing of effect in language, and a speech emotion analysis subgroup that uses linguistic information. But nowadays, it's really become more and more standard to also look at the linguistic part. It's tricky because you have to recognize speech to this end, and we've been talking about problems with that. So this is maybe a reason why it's not used on a broader basis. And yeah, there we're lacking the multilingual studies and the cross-lingual reusability of models. So there seems to be no experience. How can we translate into a meta language, be it English or whatever, and then reuse it after translation into a target language. Then we have more and more integration of non-linguistics, these laughters in size, but this is really just starting up now. We still need to integrate ASR acoustic confidences, substitute out of vocabulary events, which I've been talking about. So here's just one example for the AVEC challenge. And the AVEC challenge, I think nobody or one side only used linguistics. We did in another paper outside of the challenge and showed that for expectation and valence, in particular valence is where you would expect it, linguistic features give a lot, so you can really use linguistic features. Number 6, more optimization. In older papers, you had not seen this much of systemized or systematic classifier optimization. Now grid search, for example, is becoming more and more a standard. Feature reduction is becoming a standard, but even data optimization by balancing with algorithms like SMODE or whatever, RANSAC or things like this, to choose the right data points of interest is becoming more and more common habit. Then, of course, subject normalization and optimization, for example, by introducing speaker clustering. This is possible in speech recognition where you have months of speech or even more available. With 10 speakers in the database, hardly any point in doing speaker clustering. But now that we have these larger data sets with 1,000 speakers, we can start to do speaker clustering, for example. These are examples from the speaker state challenge for intoxication and sleepiness, showing the complexity parameter optimization for the support vector machine. And there is clearly a heap by 4%, for example, for sleepiness, and whatever, some percent for alcohol intoxication. But it's more and more becoming a habit to also report these heaps and not only say we have this and that result and report by a systematic optimization method like grid search how this was reached. Then we have more standardization. So we've already seen this. This was not a concern so far, but it's becoming one about now. In particular, more realism. So the databases are non-acted, non-prototypical, non-pre-selected. The processing is still very much handmade, partly. So for example, most of these studies based on pre-chunked speech. So you're having your offline files, and you don't have to spot it in the continuous speech stream, which will be one of the upcoming challenges. Linguistic analysis was mostly based on transcription and not on the ASR output. This is changing slowly now. Metadata has to be retrieved from the web. For example, if you're using online knowledge sources, you're exploiting online knowledge sources as they're available on the net and not your tailored list of effective words that fit the data that you have to label with, and well-defined feature sets. And evaluation is more and more becoming more realistic by using development sets and ensuring subject independence. Number 9 is more robustness, awareness, and issues. I should add to more realism and maybe to more robustness. There's one type of robustness that is peculiar to this field, and that is robustness not against technical issues like noise addition, package loss, or reverberation, coding artifacts, but it's robustness against user simulation or fiending. So we don't have studies so far trying to detect if somebody is trying to hide his intoxication, fake another age, and so on and so forth. So we would also need robustness in this sense. But what is coming up now is more robustness analysis for the noise addition, reverberation addition. I think there are hardly studies dealing with package loss, but the more we're becoming or seeing applications, maybe even using Skype or voice over IP speech, this will be of interest. Now, this is almost a lie, more user studies. There aren't more user studies. I put it here because I wish for more user studies. And that is stop reporting results on databases, but start to report how do these systems work in the real life. And if you remember, I said there is a robot guiding you around a museum, taking into account your interests from our software. We had a test for this with a fixed number of dialogue steps. So it changed exhibits always after 10 explanations. So it said 10 items about an exhibit and then brought you to the next exhibit. Then we had automatic interest detection, and then we had a Wizard of Oz that was looking at this from a distance and said, okay, now the person's really bored, you should change exhibit. And we asked many questions, including this one, some 40 subjects. Did you think the system was taking into account your interest? And we really liked the outcome, because in the case that it always had 10 things said and then changed exhibit, a third of the users said, yes, I think it took into account my interest. If you had automatic detection, 2/3 of the users felt like it did. And if you had the Wizard of Oz, well, 84% did. So the message is, it somehow works. It's better with a automatic system already. But of course, there's headroom, so we will get more funding, hopefully, in the next years. And it's completely different from looking at these, 70% for negative, positive problem on the same database that we've done many experiments beforehand. And even if we claim we've only used development set, there's always some expertise from the past, whatever. It simply shows a different picture. So I would really like to see more of these. 20 minutes left, as far as I see. Most urgent moment to switch to the practical part. There's a short introduction to the practical part, and that is what toolkits are there and how can I do this at home. So let me first say there are two tasks that we have to do in a very rough subdivision. One is the front end, the feature extraction, and one is the back end, the model training and classification. And the third thing, in order to make up for a good toolkit, would be that you have pre-trained models. Imagine you're downloading a speech recognizer. You would already want to test a little bit how well does it recognize speech. So ideally, you're having pre-trained models that already allow you to use it for emotion recognition and so on. There are two different application domains usually for such a tool. One is batch evaluation, where you write your paper, you're processing your 10,000 instances in the batch run offline, and the other one is an online real-time system that should be able to do something like this avatar. And now let's look at these one after the other. First is feature extraction. The classic probably in the field is prod. Who knows prod? Yeah, the classic. It offers many, many different feature types. It's well standardized, somewhat platform independent, so it's a great choice. Who knows snack? Okay. It's discontinued. I used it at the very beginning of my master thesis. It's a tickle extension that provides some features. Who knows the HTK? HTK is here under feature extraction because it also provides MSCCs, LPC, PLP, and energy in some feature variants. Then there are some music information retrieval toolkits that you could be using for speech analysis, like JAudio, Marzius, MIR Toolbox, and so on. Then there is Esmeralda, MATLAB toolboxes, like by Raul Fernandez. And then there is OpenSmile. So that we will have a look at now. It focuses on all these states and traits, a little bit on ASR and music information retrieval. In the name, it is already speech and music, so working on audio in a general application range, we wanted to have a toolkit that unites the two major worlds of music and speech processing, also to benefit from each other and to have a more standardized toolkit. So it has many different LRDs and many functionals. We'll look into that in more detail later on. Now the second part of it is the back end, the classification part or regression part. Who knows Weka? Almost everybody. Rapid Miner. Not so many, okay. It had a different name beforehand, yet another learning environment, or Yale for short, and it's very similar to Weka, but has some more visual approach sometimes than Weka has. Well, then HTK, of course, again. Esmeralda also has some GMMs and HMMs, RNNlib. libSVM is probably one of the most used support vector machines. And even Prod has some feed-forward neural networks, so many of these toolboxes have two of these parts. Now, in order to make up for a complete package, I said you would want to have pre-trained models. And there is hardly anything for the speaker state and trait domain that has pre-trained models. One is EmoVoice from the University of Augsburg. The feature extraction is based on Prod and Esmeralda. And there's a couple of different functionals, and it has some pre-trained models on one or two databases. And then there is OpenEar, our toolkit, the Open Emotion and Affect Recognition toolkit. The OpenSmile is the feature extraction package from OpenEar. But in addition, we have some integrated classifiers. Recently, also the long short-term memory recurrent neural networks I showed to you, and it has a very well elaborated interface to all these libSVM, HTK, and so on and so forth, GTK, and so on things. So it has a different data formats as output, like ARF for WCA, binary for HDK, comma-separated value for good human readability, libSVM output, and so on. It's supporting multi-threading and has some ready-to-use models for emotion and interest recognition, and I'll show a short demonstrator later on that was trained in all the challenge tasks, and it allows to plug in several database-trained models for all these different tasks and show you the results simultaneously, so that you can toy around with speaking one sentence but getting an output for your height, drunkenness, and personality, and so on. And we're cutting deals at this moment with all the database owners, and they all agreed so far that we may release it with pre-trained models on all these different databases, so that we have a open source, free-to-use, pre-trained intoxication, sleepiness, and so on recognizer if you should be interested in using this as a black box. So it has a modular architecture, incremental processing, some models. This is the central architecture. It has a data memory and these different processors around. Everything is kept very modular. So you have a windowing, for example, component, and you can describe how the windowing should be done. You have a data processor, for example, FFT. Then you can use another data processor, for example, the meal filter bank, and you can concatenate these one after the other to tailor your very, very handcrafted MFCCs or MFCC type features, and you can have an influence on all the parameters if you want to. There are all sorts of data processors also for the functionals and even for some speech enhancement, histogram equalization, or things like this. Voice activity detection, so there are many, many of these modules that you can use to write a script. It has a buffer incremental processing, meaning that it processing speech as soon as it comes in and updates the functionals. So for example, if you want to have the mean pitch, while you're talking, it updates the mean, and the buffer is a ring buffer that is very efficient in the sense that it doesn't recompute everything anew, but is memory efficient to keep things real-time capable. Okay. So yeah, as said, it supports different outputs, even wave, not only these feature files. As input, it supports PCM wave and different feature files, so you can also input a feature file with low-level descriptors and only use the functional level. Many people use this now to process brain signals or whatever, to use OpenSmile only as a functional toolbox. And also linguistic features can be derived from string inputs. And then it has quite some signal processing. This list is not complete. It's not necessarily up to date, but it provides all these sorts of different things, including psychoacoustic weighting and the VAD, also acoustic echo cancellations, and some sorts of mean variance normalization, histogram equalization, and so on. A bunch of low-level descriptors. If you have one that is not inside and you need it, please drop an email, and we try to include it. Bless you. It's, I said some music things here, like chroma or sense features, and many, many speech usual suspects, many different functionals, segments, peaks, DCT coefficients, and so on. And then some classifier interfaces to have a very efficient operation, in particular for libSVM, the Julius engine, HTK, and now it has online LSTM recurrent neural networks implemented itself, and we're implementing more other classifiers. For emotion, there are some pre-trained models that you can use out of the box as an emotion recognizer on the ABC Berlin corpus, the SAL corpus, and the AVIC for interest. And these are some benchmark results with the larger feature space. So these are 7 classes of emotion with 55%, 3 levels of interest, 55%, and 7 classes of emotion, 85%, depending on the database. So you can download it, start it, and get your results for your interest or emotion based on these models. As said, we're constantly integrating more new models. This is where you can download it and find the other software, openaudio.eu, or on SourceForge, but you will get the link on openaudio.eu. And now, on your stick, if you have a stick, you should have a small package including most of all the smile extract binary pre-compiled for Windows. Of course, you can compile it in Mac, under Linux, and so on if you download the source code. And there are some further scripts here that I didn't put on this stick, but which is in the download start package, so to say. And then we have some config files to look at. And this is really how it works. We're writing config files. So after all the good news, here's the bad news with OpenSmile. It's not intended to be a tool for phoneticians this much as Praat is. So there is no visualization. There is no graphical user interface. It's really tailored for real time and for batch processing, meaning that you're writing script files. The positive thing is you can distribute and exchange the script files to compare your results in a paper with another paper, but it's really based on scripts. Okay, let's see. For the things that are most important, -h, well, -help, gives you usage info. And most importantly, with -l, you can display the list of all components. So once you download the recent version, you type -l and you can read through everything that's in there. And then you can get more specific help on the different component with -h in the component. And for example, see what can the HEQ or the psychoacoustic weighting really do. And then this is how it works. We're typing smile extract -c with the config file and the -i the input file, -o the output file. And then we get for this WAV file, raw, audio file, whatever, the feature file in the file format that we want. So for example, we write -i input blah 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 dot wave, output blah 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 dot arf. It outputs the Vega file format feature file. Or you write .hdk and you get the binary HDK output format. So it should be very intuitive. There's some batch processing Perl scripts if you don't want to do this file by file, but of course you can always write your own scripts for that. Okay, so this is, before we look, let's very shortly look into it. So in the OpenSmile tutorial, you have a number of files. I don't know, can you read this at all? Probably not. Yeah, in any case, you have some files here, some WAV files. You have the OpenSmile extract executable, and you have some feature configuration files. And I can type smile extract.exe-c, specify the configuration file for the feature set, -i avic1 wave, -o avic out.arf, so we're getting it as an arf file. It processes the file, and in the folder we should now have avic out.arf, and we can look at it in the text editor, and we're seeing a Vega file format where it specifies all the features that have been extracted. And then for the single sound instance, we have all the feature values. Now, we didn't specify a class label. We can do this, but let's say it's only the class null. And then we can start this in Vega, for example, by simply clicking on our output file. And if I had specified .csv, it would have outputted it in comma-separated value. If I had said HDK and so on, it would have directly produced the right format. So now you can see our one instance, the audio file we had converted, and you can see the feature names here, and you can directly use this in Vega and look at the different features. As it's only one instance, there's not much use in looking at the distribution. But what is of interest now is, of course, the file, the configuration file. This is Interspeech 09 configuration file, so we're using the one from the Interspeech emotion challenge. And there is a first section which components are active or not. So wave in and so on, FFT and so on are all active. You can put a semicolon to make them, turn them into a comment and deactivate them. So you don't want part of these if you don't want them. And then you have the component configuration. So for each component, you're configuring simply the parameters. You can get the help on these components by specifying -HC wave source, for example, and then you get all the options that you can specify. And here you can say if it should mono mix down the audio, so it's set to true, or if it should keep it stereo. You can say the buffer size and so on. So for each of these blocks, you can have the different parameters configured. And then you have, for example, the MFCCs here. First, you do a transform to the FFT domain, and you say if it should output magnitude values or not, if it should do the FFT or inverse FFT, and so on and so forth. Then here you do the meal band mapping, and you say how many meal bands do you want to use. Should they be computed in an HDK compatible way or an open smile way? You can specify low frequency, high frequency. So in short, you can specify block by block all sorts of parameters to tailor to your need. Then you can say if the functionals should be used or not. So per functional, you can write that you consider this functional and simply say 0 or 1, turn it on or turn it off. So for example, in the Interspeech Emotion Challenge set, we had some 380 something features. We did not look at linear, we only looked at linear regression coefficients, but not at quadratic. I can now turn these all on and produce a feature file with quadratic regression coefficients, simply by setting these to 1. Now, I'm making AVIC out larger. Features are extracted. And I can look at AVIC out. So this is our old feature file, 21 kilobytes, 32 for the new one. You already see it's larger. But let's look at it in Veka. So you can see for the old original feature set, we had 386 features. Now we're looking at the feature set we extracted with the quadratic regression coefficients. Oops. And I forgot to specify a class label because and you see now we have 578 features. And what happened is that in addition to the linear regression coefficients, per feature low-level descriptor, it added the quadratic regression coefficient that we had just set to 1. So in short, it's very easy. You have the binary and you can extract your features. You can tailor your feature files to your needs and get your feature files. Now there is also the OpenEAR package that comes with the pre-trained models. And let's look at one example. So here you can see the pre-trained models on the 2010 interest task, the 2010 age and gender task, the 2009 anger task, trained on children's speech, so probably not working very well, alcohol intoxication, sleepiness, likability. Let me talk a little bit and enable the input and see what I'm like. Hello. Yeah, so I'm drunk now, as you can see, very sleepy. And yeah, let's see. Okay, now I'm sounding awake. I'm a female under 14, interesting. Maybe I should get closer to this. And you see that you can toy around with this online update. At least I'm male now, I'm interested. And let's see if I can fake some sleepiness now. So, sleepy. And we can also disable the online input so that we can have it more controlled and only allow it while I'm pressing the space. So you still see the voice activity detection, but it doesn't process it anymore. At least I have a beautiful voice. And you can see that it gives you quite a different perspective now, not only looking at one at a time, but to really see what happens if you look at several at a time and see the interdependence of these. Because once you're sounding more like sleepy, maybe another one goes wrong. And this is why I really think the most important thing probably to do now is to process them in one pass, not one by one. Now, this is exactly the last minute. Allow me just a very short 2-minute commercial break. This is, if you're interested in this, the forthcoming book I wrote with Anton Badliner, which should appear very soon. This is my forthcoming book on intelligent audio analysis, also covering music and speech recognition. There is a tutorial at the Interspeech if you really didn't get enough today. But maybe more of interest is the workshops coming on. The wide spectrum social signal processing workshop at the Social Computing. You can still submit papers in the next week, but maybe we're prolonging. The Audiovisual Emotion Challenge, you can still participate in this. And a special issue in the IEEE Intelligent Systems magazine for the sentiment analysis. Then there is Interface, a project by ours for socially aware man-to-machine communication. If you were really urgently interested in this, maybe you could still join, I don't know. But you could contact me. And then there is, of course, the Interspeech Speaker Trade Challenge. This is not open anymore, but it's ongoing. And a number of special issues that either appeared already or will appear very soon that I've been guest editing in the Computer Speech and Language on Speaker Analysis, and then the EUROSIP Journal on Advanced Speech, Signal Processing, Image and Vision Computing, Computer Speech and Language, IEEE Transactions and Effective Computing. But you will find all the information in the Special Interest Group Speech of the Humane Association. So if you go to emotionresearch.net, you can find this information. And if you go to openaudio.eu, you can find our toolkits. So by that, thank you very much for your interest.
Okay, with this session, we close the summer school. We thank you all for coming. I hope you have fun, you have learned. And as I told you the first day, I hope you come back home with your backpack full of new ideas to apply to your research. Maybe also some white wine bottle, some mussels, some empanada gallega. You can carry on also. So anything else? Try to fill the survey we put in the webpage for us to know your feedback. And as I told you also by email, next week probably, I'll send to you a link for seeing the recording lessons. Okay? The recorded lessons will be available forever. Thank you very much.